Okay, so today we will study about the combination of resistances. Okay, and we have studied that the electric circuit may contains number of resistance and the source of electric energies. The circuit current depends upon this resistance and the potential difference applied across it. Okay, a certain combination of resistances are used in the circuit to obtain the required values of current and voltages. And a number of resistance can be connected in two ways in a circuit, that is series and parallel combinations. In the series combination of resistances, when two or more resistance are connected end to end such that this is the series combination. When the two or more resistances are connected end to end, okay, end to end such that the second end of the first resistance is connected to the first end of the second resistance, and so on. The resistances are said to be connected in series between the 2 points x and y. Okay, so these resistances are connected in series between the points x and y, and here the same current flows through the each resistor. The important point to note is that in series combination, the resistance, the current flows will be the same in each resistor. That is, there is only one path for the current to flow between 2 points. There is only one path for the current to flow between these 2 points when same potential difference is applied across this combination. When same potential difference is applied across this resistance, there is only one path of the current to flow between these 2 points. Okay, so this is the combination of the series resistances. Okay, so when we combine this resistance, and the next type of combination is the parallel combination. Okay, so what does this parallel combination means? When two or more resistances are connected in such a way that the first end of all the resistances are connected to first common point. Okay, first end of all the resistances are connected to the first common point, and second end is connected to the second common point, and so on, and so that the same potential difference is applied across. Here the first point and the second point is of this combination is common, so of each resistor. Okay, so first point is joined with all the first points of the resistors, that is R1, R2 and R3, and the second point of these R1, R2 and R3 resistors are also common or same at the point Y. Okay, when two or more resistors are connected in such a way that the first end of all the resistances are connected to first common point and second end of these resistors are connected so that the same potential difference is applied across each of them, they are said to be connected in parallel. Okay, the current enters the first and leaves at the second end. Okay, first end where the x is there and the second end where the y is there, the current enters from one end and then leaves at the other end. In parallel arrangement, there is more than one path for the current to flow. Okay, in the series resistance combination, there is only one path for the current to flow. In the parallel arrangement, there is more than one path for the current to flow between the points x and y, and the current takes the three possible paths. This current takes the three possible paths, that is I1, I2 and I3 across R1, R2 and R3. Okay. Okay, so this is the way of connecting the parallel and series. Now, the resistor in series. What happens to the value of current when a number of resistors are connected in series in a circuit? So, what is the value of current? We can see here the resistances are connected here, and potential drop or potential difference V1, V2, V2, 3 are different in across each resistor. In the series combination is different. Okay. If we are using the parallel combination, the potential difference across the resistances are same, but in the series combination, the potential differences across the resistances are the different. Okay, so we will observe that the potential difference is equal to the sum of potential difference of V1, V2 and V3 Okay, we will take here the potential difference in the series combination for deriving the relation of the equivalent resistance of the or total resistance of the circuit. We will add this all the potential differences V1, V2 and V3. Thus the potential difference across a combination of resistors in series is equal to the sum of potential difference across the individual resistors. Okay, this is the sum of the potential difference across the individual resistance. Okay, V1 plus V2 plus V3, and let here we assume that the current I be the current through the circuit. The current through each resistor is also capital I. The current through each resistor is also I, and it is possible to replace the three resistors joined in series by an equivalent single resistor of resistance R, such that the potential difference V across it and the current through it we can calculate by the Ohm's law, that is V is equal to IR. So V1 is equal to IR1, V2 is equal to IR2 and V3 is equal to IR3. On adding this IR, which is V, and equal to IR1 plus IR2 plus IR3, and RS is the combination of these resistances in series, that is R1 plus R2 plus R3. When we join these resistances in series, RS will be R1 plus R2 plus R3. Okay, so we can conclude that the several resistors are joined in series. The resistance of the combination RS equals to the sum of their individual resistances. Okay, and thus greater than any individual resistance, and is thus greater than any individual resistance. Electric lamp whose resistance is 20 ohm and conductor 4 ohm resistance are connected to a 6 volt battery. Calculate the total resistance of the circuit, the current through the circuit and potential difference across the circuit. So resistance of electric lamp R1 is 20 ohms, R2 is 40 ohms here. Okay, and then the total resistance of the circuit is R1 plus R2, that is 24 ohms. Okay, and here the RS is equal to 24 ohms. Okay, the electric lamp's resistance is 20 ohm and one more resistance 4 ohm is connected in series, so total resistance will be 24 ohms. And for calculating the current and voltage, we will apply the Ohm's law. By Ohm's law, I is equal to V upon RS, that is 6 volt upon 24 ohm, 0.25 ampere. This is the current flow in the circuit, which is same in all the resistors. So we will calculate the potential difference across the lamp. If you want to calculate the potential difference across the lamp and the conductor, we will separately calculate the V1 and V2, as the V1 is the value of resistance across the conductor electric lamp, that is 20 ohms, 20 ohms into 0.25 ampere. Current will be same, that is equal to 5 volt, and across the conductor V2 it is 4 ohms into 0.25 ampere, that is 1 volt. Okay, so resistance of a circuit is equal to V upon I. Total resistance of the circuit is V upon I, that is 6 volt upon 0.25 ampere, 24 ohms. The total resistance of the circuit equal to the sum of the two resistances. In the next, the resistance in parallel. For deriving this resistance in parallel combination, we will add the values of resistance. How we join them? We have seen this circuit diagram that all the ends points are common. Here currents are different, so we will assume that the I is the total current of the circuit, and I is equal to I1 plus I2 plus I3, because in each branch in parallel the current will be different. Here potential difference will be same for each branch of the resistors. The current will be different for each branch. So Rp with the equivalent resistance or R parallel is the combination of resistance in parallel, and I is equal to V by Rp, that is the Ohm's law. So I1 across the first resistance, the current will be I1 is equal to V upon R1, and current across second resistance V is upon I2 is equal to V upon R2, and I3 is equal to V upon R3. So we have V upon Rp, that is the potential difference or the current across the parallel combination of the resistance is V upon R1 plus V upon R2 plus V upon R3. So 1 upon Rp is the equivalent resistance or total resistance of the circuit in parallel circuit, that is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3. Thus we may conclude that the reciprocal of the equivalent resistance of a group of resistance joined in parallel is equal to the sum of the reciprocals of the individual resistance. So in a group of resistance joined in parallel is equal to the sum of the reciprocals of the individual resistances. Okay, we see a real example number 12.8. Here the resistors are given R1 and R2 and R3 connected in parallel, having the values 5 ohm, 10 ohms and 30 ohms respectively, which are connected to a battery of 12 volt. Okay, now the current through each resistor we have to find, and the total current in the circuit and total resistance. So what will be the value of the current here? I1 is equal to by Ohm's law, I1 is equal to V upon R1, that is 12 volt upon 5 ohms. Okay, I2 is equal to V upon R2, that is 12 volt, because potential difference remains the same, 12 volt upon 10 ohms, that is 1.2 ampere. I3 through R3, that is 12 volt upon 30, that is 0.4 ampere. So I is equal to I1 plus I2 plus I3, that is 2.4 plus 1.2 plus 0.4 ampere is equal to 4 ampere. Now the total resistance Rp is given by, so 1 upon Rp is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3. This is the total resistance, that is 1 upon 3, and Rp is equal to 3 ohms. Here also we are given R1 and R2 in parallel, then R3, R4 and R5 in parallel combination. Okay, so what we have to find in these circuits, it is a 12 volt battery is connected to the arrangement. We have to calculate the total resistance in the circuit and total current flowing in the circuit. So for calculating the total resistance and total current, we will apply the same law of the parallel combinations. 1 upon Rp is equal to 1 upon R1 plus R2, and 1 upon Rp is equal to 1 upon R3 plus 1 upon R4 plus 1 upon R5. Okay, so 1 upon R dash and 1 upon R double dash is shown here, and these are also, when connected in parallel, they are adding in the inverse form. But when we are going to calculate the total resistance, that is R dash plus R double dash, that is they are connected in series, that is R dash plus R double dash at 18 ohms is the total resistance, and the total current through this circuit is total potential upon resistance, that is 12 volt upon 18 ohms is equal to 0.67 ampere. So we have seen that in series resistance the current is constant throughout the electric circuit, and this is impractical to connect an electric bulb and electric heater in series, because then they need different currents. Okay, they needs currents of different values, because our devices in your home needs the currents of different values. We are connecting them in the parallel combination, because in parallel combination the value of current is different. Another major disadvantage of series connection is that when one component fails, the circuit is broken and none of the components works. So if you use fairy lights to decorate buildings on festivals, on marriage celebration, etc., you might have seen the electrician spending a lot of time trouble locating and replacing the dead bulb. So each has to be tested to find which has fused or gone. On the other hand, a parallel circuit gives the circuit through the electrical gadgets. Total resistance in parallel circuit is decreased. Okay, this is helpful particularly when gadget was different resistance and different current to operate properly. Okay, so these are the series and parallel combination of the circuits. Okay, so read them and write them in your notebooks. Thank you. Have a nice day.